Hello ladies, Mrs. Blaufuss here again. This is lesson 2.7 and it's about using absolute value functions and transformations. So we have a few key vocab terms. The first one is absolute value function. So we learned about absolute values where the absolute value of x if x is positive, negative x if x is negative, and 0 if x is 0. So we can define our absolute value function as f of x equals the absolute value of x. The next term is a transformation, and a transformation is anything that changes a graph's size, its shape, its position, or its orientation. There are several different types of transformations, and in this lesson we talk about a couple of them: translation and reflection. A translation is a transformation, one of the two that we talk about in this lesson. It's a transformation that shifts the graph either horizontally or vertically or both, but the size, shape, and orientation are all remain the same, unchanged. And another type of transformation that we talk about in this lesson is a reflection. And a reflection is a mirror image. However, we can have reflections that are also vertical stretches or vertical shrinks. But the generic definition that we're going to give for reflection is when a equals -1, the graph of y equals a times the absolute value of x. So in this next part, we're going to look at the absolute value function. So the absolute value, remember, is we have the absolute value of x equals x if x is positive. It equals 0 if x is 0. And it equals the opposite of x if x is already negative. Our absolute value function is f of x, the function of x, equals x if x is positive, 0 if x is 0, and negative x if x is negative. So a key concept that comes right from your textbook talks about parent functions. The parent function of all absolute value functions is f of x equals x. That's our very general, generic, all-encompassing parent function. And then we'll add other things, like in the last slide we saw reflection functions, or we can look at translation functions also. But the parent function is f of x equals the absolute value of x. It looks V-shaped, it's symmetric about the y-axis, meaning if x is -2, the absolute value of x is 2. So the y's are always positive with our parent function. So it reflects over the y-axis. So our graph looks like a reflection about the y-axis. So every point xy on the graph, the point -x, y is also on the graph. The y is the same, function is the same, but as the x's go negative, the absolute value of that negative number is still positive. So looking at our graph, we see a vertex point, and the vertex is either the highest or the lowest point on a graph. And in this case, we have the lowest point of our parent function for absolute value at 0, 0. So with our parent function, the vertex is going to be a minimum, and the vertex of function of x equals the absolute value of x is 0, 0. In the last slide, we saw our parent function of an absolute value function, but there are also child functions of this, and those are vertical shifts or horizontal shifts, or vertical stretches or horizontal stretches. And on your note sheet, you'll see a vertical shift. It says left or right, but a vertical shift actually is up or down. So you can edit that on your note sheet. A vertical shift up or down or horizontal shift, left or right, is called a translation. The graph is translated h units horizontally. Looking at this graph of an absolute value function of beyond the parent function, the graph is translated h units horizontally and is translated k units vertically. Translations can be used to change the position of the vertex. So again, in the last slide, we saw the vertex at 0, 0, but that's not going to be true for every absolute value function you see. So when we translate an absolute value function, we change the vertex and we change it to the point hk. So the number of units that it's translated horizontally are x values, and the number of units that it's changed vertically are y values. So in the first example, we're going to sketch a graph of y equals the absolute value of x minus 1 plus 3, and then label the vertex. So the first thing we're going to do here is we are going to plot the vertex. So our vertex is translated 1 unit horizontally and 3 units vertically. So first we're going to identify our vertex. And our general equation is y equals x minus h plus k, the absolute value of x minus h plus k, with h units translated horizontally. So our h in this case is 1, and k units vertically. So our k in this case is 3. So here's our new vertex. So we're going to plot that point, 1, 3. Then our second step is to plot another point on the graph. So I'm going to use x as 0, for example. So 0 minus 1, the absolute value of that is negative 1. 0, oops. 0 minus 1 plus 3. Negative 1, absolute value of negative 1 plus 3. I get y equals 4. So 0, 4. And then the next step is to use symmetry to plot another point. So if 1, 3 is our vertex, then our line of symmetry is x equals 1. And point 2, where x is 2, y is also going to be 4. So every time I go up an x, I'm also going to go up a y. My slope for this equation is 1 for this line and negative 1 for this line. So you want to find the vertex, you want to plot another point, and then use symmetry to plot a third point, and then you can connect your points. So here's what my graph would look like. Now on your own, pause the video while you work, sketch the graph y equals the absolute value of x plus 2 minus 1. Remember that the generic formula, you can look back at your notes, is y equals the absolute value of x minus h plus k, where h is the number of units shifted horizontally and k is the number of units shifted vertically. So to start, I want to find the vertex. And to do this, I'm going to look at my h, which is, in this case, -2, because x minus h is my general. And now I have x plus 2, so my h has to be -2. And then my k is -1, because generally I have plus k, and here I have -1. So my vertex is -2, 1, and I'm going to plot that point. Next, I'm going to pick another point, and I chose to plot -1, where x is -1, because it's right next to the vertex. So when x is -1, my y is 0. So now I'm going to plot that point. And then next, I'm going to use symmetry to find my third point. And if I use symmetry to find my third point, I can plot x, where x is 0, y is -1. And then I can connect my points to create my absolute value function graph. My vertex, again, is when x is -1, oops. Just realized I made a mistake, so I had to clear out my lines. My vertex actually is when x is -2, y is -1. So here's my vertex that I labeled up here, -2, -1. And then my second point that I graphed was when x is -1, y is 0. So here's my second point that I plotted. And then I made a mistake when I was using symmetry, because here is actually my line of symmetry. So my third point that I should have plotted was when x is -3, y is 0. Now I can connect my points to create my absolute value function graph. So here's what my graph should look like. So now looking at another child function of the parent absolute value function graph, if we add in this a like we did on our first slide with our definitions. So if you look back to your first slide, y equals a times the absolute value of x is a reflection in the x-axis of the graph. Y equals the absolute value of x when a is -1. So our a is going to be a coefficient that tells us reflection and other transformations, including vertical shrinks and vertical stretches. So for the absolute value of a, when that is greater than 1, the graph is vertically stretched, and y equals a times the absolute value of x is narrower than the graph of y equals x. So if you can imagine, here's your y equals x graph. Here's your vertex. If the absolute value of a is greater than -1, it's stretched and it's narrower than the graph of y equals absolute value of x. If it's less than 1, the graph is vertically shrunk and it's wider. I'll do it in green. So here is a vertical shrink. It's wider. It's lower. And here is a vertical stretch. It's narrower. It's taller. So it first asks me to graph y equals 0.5 absolute value of x, and b, y equals -2 absolute value times the absolute value of x. Compare each graph with the graph of y equals the absolute value of x. First thing I'm going to do is for a and b, I'm going to graph y equals the absolute value of x. The graph y equals 0.5 times the absolute value of x is vertically shrunk by a factor of 1/2. So the graph has a vertex of 0, 0, but it passes through -4, 2, and +4, 2. If I plug in 4 to the graph y equals 0.5 times the absolute value of x, and I plug in -4 for x, I get a y value of 2. And if I plug in +4 for x, I get a y value of 2. So here's what my 0.5 times the absolute value of x function graph would look like in the green. Looking at the second graph, y equals -2 times the absolute value of x. First, I know that it's a reflection over the x-axis because my a is negative. And secondly, I know that it's a vertical stretch because it's less than -1. So therefore, the absolute value of a is greater than 1. If you look back on your last slide, the absolute value of a is greater than 1. It's a vertical stretch. So if I pick a couple points on my graph, and I chose 2 and -2, if x is 2, then y is -4. And if x is -2, then y is -4. So on graph B, you can see what the graph should look like for y equals -2 times the absolute value of x. Now on your own, graph the equation y equals 3 times the absolute value of x. Is it a vertical stretch or is it a vertical shrink? And what is the vertex? So here's what your graph should look like. The purple is the parent graph. And so just so you can compare, the green is the graph y equals 3 times the absolute value of x. So 3, that's our a. And the absolute value of our a is greater than 1. That means it's a vertical stretch. And if you picked a couple points for x, I chose 1 and I chose -1. My y for both of those, x is 1, y is 3, x is -1, y is 3. In this next example, it asks you to compare the graph with the graph of y equals x for the graph y equals the absolute value of x plus 4 minus 2. So remember our vertical shift and horizontal shift formula. We have x minus h, the absolute value of x minus h plus k. And we can come up with our vertex of this shifted graph. And our vertex is our x is -4, and our y of our vertex is -2. In this function, I don't have an a, so it's just a vertical and horizontal shift. It goes 2 units down and 4 units to the left. So I'm going to graph both my y equals the absolute value of x and y equals the absolute value of x plus 4 minus 2 graphs. So I've graphed my absolute value of x function in the purple, and then I found another point on my translated function. I chose to look at when x is -3, and my solution was y equals -1. My vertex is -4, -2, so then I can use symmetry to find my x is -5, y is -1. And in the green, you can see the graph of the translated function. Now looking at a graph of an absolute value function that has a vertical shift, a horizontal shift, and a vertical shrink or a vertical stretch, and a reflection, we can see the graph y equals -3 times the absolute value of x plus 2 minus 1. And we're going to compare that graph with a graph of y equals the absolute value of x. So the first thing you want to do is identify the vertex. And to do that, you can rewrite the function so that you follow the rules of the absolute value of x minus h plus k. So here you can see that we rewrote the function y equals -3 times the absolute value of x minus a -2 plus -1. So we know that the vertex is -2, -1, where h is -2 and k is -1. So when it asks me to compare the graph to y equals the absolute value of x, the first thing I'm going to do is graph that, y equals the absolute value of x. Then the next thing I'm going to do is plot my vertex, -2, -1 of my new function, y equals the -3 times the absolute value of x plus 2 minus 1. Then I'm going to choose a second point on my new child graph, and I'm going to choose x is -1 and solve for y. And when I solve for x is -1, y equals -4. So I'm going to plot that point, -1, -4, and then I'm going to use symmetry to plot the point -3, -4. So my x is -3, my y is -4. And then I'm going to connect my points to draw my translated and transformed and reflected and shift and stretched new graph. So below you can see what the new graph looks like, and it's in green. We can first see that it's a reflection because our a here is a negative number. And secondly, we can see that it's a vertical stretch because the absolute value of our a is greater than 1. The next example asks us to write an equation of the graph that's already shown for us. So the first thing we're going to do is identify the vertex, which we see the vertex at 3, 2. And the second thing we want to do is identify any vertical stretch or vertical shrink. And in this case, we see a vertical stretch, and we also see a reflection. So we know our a is going to be negative, and we know the absolute value of a is going to be greater than 1. So going beyond this first equation that we have, where y equals the absolute value of x minus h plus k, this is just a general equation for a horizontal and vertical shift. But we have this new general formula, y equals a times the function of x minus h plus k. So first we can identify if it's a stretch or a shrink. And if the absolute value of a, which does not equal 1, if the absolute value of a is greater than 1, then it's a stretch. The absolute value of a is less than 1, it's a shrink. Secondly, we can identify if it's a reflection. If a is less than 1, if a is less than 0, so if a is negative, it's a reflection. And thirdly, how is the graph translated? We can look at our h and our k to determine how many units it's translated up or down, and how many units it's translated left or right. So again, looking at our graph, we can start with y equals a times the absolute value of x minus 3, our x vertex point, plus 2, our y vertex point. And then secondly, we can identify our a as first of all being negative because it's a reflection. The absolute value graph goes down, for our y values decrease as our x values increase and decrease. And secondly, we can see that it's a factor of 2 because our normal absolute value graph looks like this. But for this absolute value graph, we see that it goes down, our y values decrease twice as fast as our x values. So when our y value goes down 1, our x value goes down, or when our x value goes down 1, our y value goes down 2. And when our x value increases 1, our y value increases 2. So here you can see the equation y equals -2 times the absolute value of x minus 3 plus 2 is our equation for our vertically stretched, horizontally and vertically shifted, and reflected absolute value graph. Now on your own, and you can pause the video while you work, graph the function y equals -1/2 times the absolute value of x minus 1 minus 2, and compare your graph with y equals the absolute value of x, and you can unpause for the solution. First thing I'm going to do is graph my absolute value of y equals the absolute value of x function, and then secondly, I'm going to find my vertex of my new function -1/2 times the absolute value of x minus 1 minus 2, and I'm going to plot that point. Secondly, I'm going to look at my equation, and I'm going to realize that this is going to be a reflection because my a is negative. And secondly, I'm going to know that it's going to be a vertical shrink because the absolute value of my a is less than 1. Next, I'm going to find another point on my graph, and I'm going to choose a point that's 2 units away from x is negative, 2 units away from x equals 1. So I'm going to choose x is 3, and when I do that, I get y equals -3. And then lastly, I can use symmetry to identify a third point. And the third point that I identify is when x is -1, y is -3. And lastly, I'm going to connect my points and draw my graph. And so in the green, you can see what my new graph is going to look like. It's a vertical shrink, it's a horizontal shift, it's a vertical shift, and it's a reflection. And then lastly, you can try this last one on your own. Write an equation for the graph shown. Please unpause for the solution. So again, here's our general equation for an absolute value function that has a vertical or horizontal shift and a vertical shrink or stretch. So I can begin by identifying my vertex, which is -1, 3. So I have y equals a times the absolute value of x plus 1, because it's minus h. So it's plus 1 plus k, which k in this case is positive. So I have plus 3. And next I want to identify my a, which I can look at the slope of both of those independently, both of those lines that are reflected over the y equals -1 line. And I can look and see whether or not this is a reflection of the parent function y equals the absolute value of x. So I can see that there's no reflection, so I know that my a is positive, and I can see that the slope of half of the absolute value line here is 2. So for every time x increases 1, y increases 2. So it's a vertical, I can see that it's a vertical stretch because it's narrower and the y values increase faster. So my new equation for this line is y equals 2 times absolute value of x plus 1 plus 3. We will continue to work with graphs and creating functions and creating equations of graphs in class next time I see you. But please jot down any questions that you have or star any pages that you didn't quite get as we went through it together or here on this video, and we will go through it together in class. Thanks, ladies.